All right, students. Good morning, everyone, or good afternoon. I just wanted to teach this lesson to you. You don't need to sign into this. This was just a way for me to open up this lesson. Please cut down today's teaching point. I'll be able to explain how air temperature is measured, identify the factors that influence it, and analyze how changes in air temperature impact weather patterns and the environment. All right, so this is going to be now your first basic understanding of weather variables. All right, this is going to begin with some of the difficulty because the weather variables are all related, they're all interconnected with each other. Launch. Think about how air temperature affects your daily life. What activities, decisions, or events depend on knowing the temperature. List as many examples as you can. All right, so you can pause the video here, think about an answer, and then you can hit the play button to listen in. All right, so temperature affects our daily life by what we have to wear or what we want to wear. When we have our summer in the northern hemisphere, we're going to dress in less layers. Right? We're going to have maybe a pair of shorts, t-shirt, maybe have a pair of sandals or flip-flops, and that might be the extent of what we would wear in our summer. All right, but as the temperature begins to decrease, going from our summer to our fall, right, we begin to put on some layers, right? Maybe our t-shirts become long sleeve shirts. Um, maybe our shorts now become pants, right? And then maybe our sandals become sneakers, right? And then as we transition from fall into winter, for the winter season, we want to dress in layers, right? We want to have like uh, maybe a t-shirt followed by maybe a sweater on top of that, or something that's a little bit heavier than just a long sleeve t-shirt. Right, we may want to wear a pair of thermals underneath our pants sometimes, right, to keep and retain our heat. And maybe those sneakers become a more insulated sneaker, or maybe like an insulated boot, especially if you're doing a lot of outdoor activities, outdoor walking, or even exercising, right? Maybe you're doing like a hike or something. And then once we transition back from winter into spring, right? We use less layers. Maybe go back and resort to having our long sleeve t-shirts, maybe a pair of pants, and maybe a pair of sneakers now. All right, so the way we dress or is dependent upon seasons, right? So if you vacation in places, like we know that places south of us going toward the tropics are definitely much warmer than conditions north of us. So depending on where you travel, right, you want to figure out um, what season it's going to be in, whether it's in the northern versus southern hemisphere, and what are the typical climate conditions for that latitude that you're going to go visit. All right, so we have air temperature. Air temperature is a measure of the average kinetic energy of the particles in a body of matter, a measure of how hot or cold something is. Kinetic energy, we visited that in our previous lesson. Kinetic energy is the energy of movement of particles. And this movement of particles can be measured in either degrees Celsius, degrees Fahrenheit, and Kelvin. All right, and the instruments that we use is a thermometer. And I'm sure all of you have seen thermometers in the past, especially if you get sick and your parents did take your temperature, or you take your own temperature. That will indicate if you have a fever or not. Right, the average body temperature is 98.6 degrees Fahrenheit. So sometimes your body can be fighting an illness in which that will increase your body temperature, and that indicates that you are ill and not feeling well. Few more things to revisit here. Celsius is based on properties of water. At 0 degrees Celsius, that temperature, that number, will indicate if water will either melt with energy being transferred in, or freeze if energy is being transferred out. Okay, versus 100 degrees Celsius, at that temperature, water can condense if energy is taken out, or if energy is put in, it will evaporate. All right, so most of the world uses Celsius. We do not. We use Fahrenheit. So temperature of 32 degrees Fahrenheit is similar to 0 degrees Celsius. Temperature of 212 degrees Fahrenheit is very similar to 100 degrees Celsius. Now, the importance of Kelvin is absolute zero. So we can see these very cold temperatures of negative 100 degrees Celsius, negative 148 degrees Fahrenheit. These are really cold temperatures. And this is a positive 173 Kelvin. So if you want to go to 0 Kelvin, right, this would be further down on my temperature chart here. And as we go further down on Celsius, it's going to get colder, much colder. As we go down in the same direction for Fahrenheit, that's also going to get colder as well. So that temperature for Kelvin is when all matter stops moving. That's the importance of Kelvin. All right, moving on, we have temperature versus volume. Warm air masses, we have expansion, volume increases. Cold air masses, contraction, volume decreases. In this example here, this picture is showing a 10-degree interval increase going from left to right, or a 10-degree interval decrease going from right to left. All right, so going from left to right, we have 10 degrees Celsius, right? We can see that the volume of this balloon is small. And as you increase the temperature, now the volume becomes bigger. And then maybe at 30 degrees, the volume is at its max for that particular balloon, right? Because that balloon can only hold so much before it may pop if you continue with this temperature increase. So as you increase your temperature, your molecules in an air mass is able to get bigger or move apart from each other. That's energy being transferred in. Right, that's the expansion. However, if you're going to remove energy and take energy out, your temperature is going to decrease. And your molecules of the air in this balloon is going to get closer and closer and closer together, giving you a smaller volume. All right, next, temperature versus density. All right, so now going back to the beginning of the year when we had our first few labs 1, 2, and 3. Within there, I think our first lab, we mentioned that the density of a material will always stay the same unless temperature and pressure changes. All right, now we're going to be dealing with temperature differences. Going with our same example here, we can see that the volume is going to decrease as it gets colder, and the volume increases as it gets warmer. Going back to those labs, our equation for density is mass over volume. So what changes here, it's the same mass, right? We're not going to be losing any air molecules in these balloons. Let's make it easier on ourselves. Let's say, for instance, we have 5 grams of air in these balloons, in all 3. All right, and let's say this one here at 30 degrees Celsius. Let's say, for instance, this is all now 5 cubic centimeters. 5 grams over 5 cubic centimeters will give us 1 gram per cubic centimeter. If I jump now to 10 degrees Celsius, let's say the volume now decreases. Let's say it's half the size. So half the size of 5 is 2.5. 2.5 cubic centimeters. But I also have the same mass of 5 grams. Right, and that's going to change our volume. Our density, excuse me. All right, so when we have 5 divided by 2.5, right, that will give us a density of 2 grams per cubic centimeter. All right, here we had 1 gram per cubic centimeter. Here we have 2 grams per cubic centimeter. So in real life scenario, right, as a weather person, as a meteorologist, this person will say when these air masses will collide, if a warm air meets a cold air mass, and that happens all over the world, especially in the United States, our warm air mass, because it has a lower density, will rise, and our cold air masses, because it has a higher and greater density, will sink. Right, that's the importance now, how temperature plays a role with the movement of air. All right, one more important thing before I roll into density. All right, as altitude or elevation increases in the troposphere, the temperature decreases. Now, this was a picture from the old reference table of last year. So we have 4 layers of the atmosphere. We have the troposphere, which is going to be at sea level. That is where we function. That's the air that we breathe. When you fly from one destination to another, you're probably flying strictly in the troposphere. If you're going far distances, like if you're heading to Europe or Asia or maybe Southeast Asia, if you're going to Australia, those far away destinations, maybe somewhere in the Middle East, those destinations you might be hitting into the stratosphere, or the lower portions of the stratosphere. Anyway, so the troposphere is what we experience day to day. The stratosphere is above our troposphere. Our mesosphere is above the stratosphere, and the thermosphere is above the mesosphere. So, as we increase elevation, and you may have experienced this if you ever go hiking and you're going to higher altitudes, right? I know my family and myself, we went to Acadia National Park, and we drove up to Cadillac Mountain to see the sunset, and my God, that was beautiful. We had to drive pretty high up. I think the elevation was around maybe 17 or 1800 feet above the surrounding area. And it was colder up there, right? It was the summertime when we went there. It was the kind of the dog days of summer, very hot conditions. All right, so we were, when we were hiking, at the base levels of Acadia, we had shorts on, we had a t-shirt, we had long socks to prevent any tick bites, and we had our hiking shoes. But we went up to Cadillac Mountain to see that's beautiful sunset. We had we had pants on, a jacket. It got cold up there, especially once the sun went down. Even colder, of course, right? Because the Earth cannot absorb any more of that radiation from the sun. Thank you, Earth's rotation. All right. Anyway, all right. So the higher you go, the colder it gets. All right, and that's because air pressure is always pulling the gases down towards sea level. All right, so you're going to have the most friction happening at sea level. That's why we have a average temperature here of 15 degrees Celsius for our sea level or the lowest altitudes that we can have. All right, and then as you increase there, it's going to get cooler and cooler and cooler because the air masses, right, become less and less and less. And we have a change in temperature in the stratosphere. It's going to get warmer, right? From roughly about from negative 55, that's at the very top of the troposphere, also known as a tropopause, to the very top of the stratosphere, aka stratopause, at 0 degrees Celsius. So you have an increase in temperature. All right, and that can be due to the types of molecules that are found there and what they can absorb when our sun gives off different types of electromagnetic energy, right? Our sun gives off all the different types: gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. So there are certain types of EM energy that certain molecules can absorb, and that absorption can make it become warmer, or if there is less absorption, it can make it cooler. So we have some absorption here of some particular EM energy, which will increase it. And then we don't have the absorption of this, so we have a decrease of temperature going from the top of the stratosphere to the bottom of the mesosphere, right, aka the stratopause, to the mesopause, which is going to be the upper portion of that. Goes from 0 degrees to negative 90 degrees Celsius. Right, from there, we probably have some sort of absorption of EM energy, which will give us an increase in the thermosphere, and this will extends to 600 kilometers. So it's a pretty big extension as you get closer and closer to away from Earth and going into space, outer space, around us. All right, so we have stratosphere, we have increase in temperature, mesosphere decreases in temperature, thermosphere increases in temperature. All right, we're going to probably stick with the troposphere for a lot of this because that's where all weather occurs, within the troposphere. We do have some weather in the lower portions of the stratosphere, but the majority of our weather happens to be in the troposphere.
You may not realize it, but from the moment you got out of bed today to the point where you sat down to watch this video, you've essentially been swimming. Why? Because air is a fluid just like water. It has waves and eddies, it flows, and when you push air out of the way, it rushes around you into a wake. So why don't we notice it most of the time? We commonly think of air as empty space. But while 1 cubic centimeter of interstellar space, the volume in the tip of your pinky finger, contains roughly 1 atom, the same volume of air has about 10 quintillion molecules. If that sounds hard to wrap your head around, it happens to be about the same as the number of insects alive on the planet, all crawling, climbing, and flying over each other in an enormous, tightly packed swarm. When this swarm of molecules runs into things, it exerts a force, pressing against the boundaries of the fluid like water pressing against the glass of a bottle. This is known as air pressure. And while air is lighter than water, all those molecules still get pretty heavy, with the total air filling a typical school gym weighing about as much as an adult elephant. So when you walk into a gym, how come you're not immediately crushed by the elephant of air in the room? Well, first of all, because most of it is pressing on the floor and the walls. And the part that is pressing on you is pushed back by the pressure inside you. You see, the air, as well as the water and everything else that fills our bodies, exerts an amount of pressure equal to that of the air outside. Of course, this is no accident. It's precisely what allows us to survive in the normal atmosphere, and what makes it more difficult at high altitudes or deep water. And we normally don't feel the air pressing on us because it's generally uniform. So even though different amounts of air molecules are hitting you at different times, the swarm is so thick that all those little differences average out. What happens when air pressure isn't uniform? This means that the molecules are pushing harder in one region of air than another, driving the airflow from the higher pressure region to the lower. We feel this flow directly as wind, and the pressure systems that meteorologists are always going on about are responsible for other weather changes, from the mundane to the catastrophic. But differences in air pressure do more than just let us complain about the weather. They're the very reason we're alive. We breathe by lowering the pressure in our lungs, allowing air to rush in. So the next time you take a deep breath, think of the unfathomable number of air molecules you're commanding to move. We look up at the night sky to ponder the infinity of space. But unless you're watching this video from that deep space, there are more air molecules in and around your body than there are grains of sand in all the world's beaches and deserts, stars in the visible universe, or both of those numbers combined. The vastness of the universe is right in front of you and inside you.
All right. I want to transition a little bit into air pressure. All right, so atmospheric pressure or air pressure, the pressure due to the weight of the overlying air pushing down on any given area, right? This is due to gravity, right? Gravity is always pulling air masses down, right, or air molecules, but because of density differences, air masses can rise and sink. All right, so atmospheric pressure is also known as barometric pressure. All right, I'll touch upon pressure with you a bit more for next class.
And it's part of the Year 9 science curriculum. What we're going to do is we're going
All right, now this is cool. So what's happening here is they have a burner underneath this canister. We can see steam, right, coming out from this canister. And that steam is water that's boiling, right? So when you heat things, we know that we can have expansion of molecules. So what's happening here is that the air masses are beginning to expand within this container. All right, and what's going to happen is they're going to cap this to keep the rest of the air inside of it. All right, so they're taking away the heat source. Right, he is going to be capping that. So we're going to see less steam coming out. All right. Now you see the hose in the background, and they're going to spray cold water on this. Right now, again, the air inside this canister has now expanded. They were heating it. Now they're going to put cold water on, which is going to make the molecules move a bit slower. and the volume will decrease. And the air around this container will begin to push around it, making a change in pressure. All right, so cold things compress or contract. All right, a few more things here. All right, so we have warm air masses expand and rise. Because you're able to expand and rise, rising air masses will have a lower pressure. Right, there's less pressure exerted on the Earth when you have air masses that rise. Right, and cold air masses contract and sink, higher air pressure. All right, so when air masses get cool and sink, it's exerting a greater force on the Earth's surface, giving you a higher pressure on the ground. All right, so when we hear about low pressures and high pressures, we're dealing with what it's like at the surface and how that can be interacting now and creating other variables that happen. All right, the last slide I have is some questions, a time to climb. So you can definitely go into this lesson that I will post for you, and you can answer some of those questions for today. All right, have a great rest of your day, and thank you for listening.